Okay, so today we will see another problem of method of images. So the problem is a point charge, a point charge in front of a grounded conducting sphere. Grounded means the conducting sphere is maintained at potential V equal to 0. Okay, so we have a conducting sphere. This is a sphere. This is the center of the sphere, and this is a conducting sphere, and this is grounded. That means the potential V is equal to 0 inside the sphere and also on the surface of the sphere, and the radius of the sphere is capital R. This is the radius, so this is capital R, and we have a point charge plus Q located here. This is the center of the sphere. Now from the center, at a distance of S, this is the distance. S is this distance. Now at a distance of S from the center of the sphere, we have a point charge plus Q. So this is our system or problem. Now the problem is to find out the potential in the region outside this sphere, because inside the sphere the potential is already given. It is V equal to 0, and also since a conductor is an equipotential, so on the surface of the sphere also the potential is 0. So our problem is to find out the potential in the region outside the sphere. So this is our problem. Okay, now we will solve this problem by the method of image. Now, like our earlier case, we will assume that there is no such sphere, and instead there is a image charge. Here we will consider a image charge which is a point charge, and we will place it inside the sphere. So we assume that, so this is the center, this is the center of the sphere, suppose O, and here is the point charge Q, and this distance is S. This distance is S. Okay. Now here this distance is suppose small a. This distance is suppose small a. Here we assume that we have a point charge Q dash, and Q dash is such a charge that Q dash is equal to minus Q into R divided by S. That is, this image charge which we are considering, that Q dash is minus Q, this Q is this Q, and into radius of this conducting sphere R divided by the distance S. So image charge we take to be a negative charge whose magnitude is q r by s. And also this distance a we take as r square by s. So this distance a is r square by s. Now from here you can see that as is equal to r square. Now s is greater than r because this distance q is outside the sphere, so s is greater than the radius of the conducting sphere. So since s is greater than r, so a must be less than r. Otherwise this product a into s cannot be equal to r square. So a is less than r. This implies that the image charge which I am considering, that is lying in the region inside the sphere, but in this case we are assuming that there is no such conducting sphere. We have only 2 point charges, one plus q here and another is q prime, which is given by minus q r by s. So we have replaced the original problem by this 2 point charges problem. Okay, now we will calculate the net potential at an arbitrary point. Suppose this is a point P. I am taking it arbitrarily. Now I will write down the potential at this point due to q prime and q. So we need these distances. And this distance we need. Okay. Now this distance also I need. So this is a. So this distance is a. Okay. Now OP I am calling to be small r. O to P I am calling to be small r, and Q to P I am calling it as this curly r, and Q prime to P I am calling it as curly r prime. Okay, and this angle I am considering to be theta. So this angle is theta. Okay. Now we can write down the potential at point P due to the two charges. Now the net potential due to q prime and q is given as V equal to 1 by 4 pi epsilon 0, that I can take common. Then q prime divided by this distance, that is r prime, plus q divided by this distance r. So q divided by r. So this is the net potential at point P due to q and q prime. Okay. Now we will see that this potential will satisfy the boundary conditions and also agree with the fact that we have a point charge q here. Now what are the boundary conditions? Boundary conditions. Boundary conditions, there are two boundary conditions. Now see, our original problem is I have a sphere here, conducting sphere of radius r. So, and a point charge q is sitting here. This distance is s. Now, we are interested to calculate the potential outside the conducting sphere. So, this region of interest is bounded by the surface of this sphere and the surface lying at infinity. So, the two boundaries, one boundary is the surface of this sphere and another boundary is the surface lying at infinity. Now, on the surface of the sphere, potential is 0 because the sphere is grounded. So, on the at small r equal to capital R, small r means the distance from the center of the sphere. This is our point P. So, this is small r. Now, when small r is equal to capital R, we come on the surface of this sphere. Therefore, when small r is equal to capital R, V is equal to 0, and 2, when this point P is at infinity, that means small r is infinite. When r tends to infinity, V tends to 0. So, these are the two boundary conditions, and we will see that this expression of the potential satisfies these two boundary conditions and also agree with the fact that we have a point charge q here. Okay. Now, we will modify this expression with the help of this theta angle, law of cosine, we will use. So, now, if you consider this triangle that is POQ, then I can write by using law of cosine, I can write r square, this r square is equal to small r square plus s square minus 2r into s cos theta, this angle between this line and this line, that is cos theta. So, therefore, r is equal to root over r square plus s square minus 2rs cos theta. Okay. Now, I will write r prime. Now, you consider triangle POQ prime. This small triangle we are considering. So, r prime I can write as root over r square plus s square minus 2ra cos theta, because this angle is theta. So, similarly, I can write down r prime is equal to root over r square plus s square minus 2ra cos theta. So, this is our r prime. Now, I will put these two expressions in the expression of the potential. So, our V becomes, V is equal to 1 by 4 pi epsilon 0. Now, first I will write this term q by r. First I will write this term, we have a plus sign. So, q divided by this r is given by this expression. So, root over r square plus s square minus 2rs cos theta. Okay, then I will write this term. Now q prime I have given, q prime is minus r by s into q. So minus r by s into q. Okay, so here we have a small space, so I will write it here. So minus q r by s divided by root over r square plus s square minus 2ra cos theta. So this is the expression of the net potential. This is q, this is q. So this is the expression of the net potential at an arbitrary point P due to the 2 point charges q and q prime. Okay, now we will see whether this expression of the potential is satisfying our boundary conditions or not. Okay, so if you put, see, first boundary condition is at, we will see what happens when we put small r equal to capital R. See, if you put small r equal to capital R, okay, now I have to put the expression of A here, then it will be simplified. So V, so I will see the boundary condition later. So V, let me simplify it more. So 1 by 4 pi epsilon 0, then bracket Q divided by root over r square plus s square minus 2rs cos theta. Then now I have r by s, this I can take inside in the denominator and insert it inside the root. So it will insert as s square by r square. So it will be minus q divided by root over. Now if I insert r by s inside the root, so it will be s square by r square, then I have small r square, then plus s square. So s square by r square will be there. Now what is A? A is r square by s. So I have a square here, so I will have r to the power 4, so into r to the power 4 divided by s square minus 2, this s square by r square will be there, s square by r square, it is coming from the numerator. Then small r, A is capital R square by s, then cos theta. So bracket close. Okay. Now we see that we can cancel some terms here. So now here we have r to the power 4, here we have r square. Now a square will cancel. Here also r square will cancel. This s will cancel one s from here. So v is modified as v equal to 1 by 4 pi epsilon 0 q divided by root over r square plus s square minus 2rs cos theta minus q divided by root over. Now I will write this term first. Here s square cancels. Now I have r to the power 4 r square. So I will have capital R square plus, now I will write this term. This is rs by capital R whole square. Okay, and see r square cancels. 1s from here cancels. So we will have minus 2 rs cos theta. So this is our expression of the potential, which we have written in terms of small r, small s, capital R and theta. Okay. Now let us put small r equal to capital R. Now if you put small r equal to capital R, so V at small r equal to capital R, this is equal to 1 by 4 pi epsilon 0. So Q divided by root over, small r will be capital R, so r square plus s square minus 2 capital Rs cos theta, then minus Q divided by root over this r square. Okay, now I will write in place of small r, I will write capital R. So this capital R will cancel, so I will have s square, then here I will write capital R, so minus 2 rs cos theta. So we see that these two terms are same, so they cancel.